Welcome back. Let's go ahead and take a look at how you might have answered part B. All right. So what we're going to look to recognize here, this is sort of like a binomial problem inside of a binomial problem. If you look at part B, think about what you would define as a success here. They get 10 shipments. The overarching success would be that the shipment or an individual shipment has at least one defective item, right? So we can classify each of the 10 shipments as either success or failure. Each of the 10 shipments can be either, each of 10 shipments we can do what? Can contain either at least one defective item. That would be a success. At least one defective item. That would be our success. What's the probability of success here? What's the probability of success? The probability of success, let's just go down here for more space. Probability that a shipment, an individual shipment, contains at least one defective item. We found that in part A. That's exactly what we did in part A because it's testing exactly 20 devices. So a success probability here is 0.4562. Each of the 10 shipments can contain either at least one defective item, that's a success, or not. Or not. And that would be a failure. That would be a failure. With failure probability Q equal to 1 minus 0.4562. What is 1 minus 0.4562? Need a calculator. That was too far away. I had to go up and grab that. 1 minus 0.4562. I've got 0.5438. 5438. There we go. Now this is really just another binomial distribution. I can say maybe I'll use the letter Y here just so I don't reuse the letter X. We want the probability of getting exactly 3 of the 10 shipments here. So 3 successes out of 10 with success probability 0.4562, whatever notation you're going to be more comfortable with here. I tend to just work with probability that equals 3 here. There's 10 shipments. Choose 3 of them to be successes. Your success probability is 0.4562. Cubed, there's 3 successes. The rest are failures. Failure probability is 0.5438. There are 7 failures, and so we run that through a calculator. Round it off to about 4 places. I've got about 0.1602. 0.1602. Quick follow-up question. What is the expected number of shipments in, how many shipments did we have? In 10. What's the expected number of shipments out of the 10 to contain at least one defective item? What is the expected number of shipments out of the 10 to contain at least one defective item when you're testing 20 devices? This is asking for the mean here, right? This is asking for the mean or the expected value, right? And that is n times p. So here we have 10 trials. Success probability is 0.4562. So we would expect there to be about 4.5 shipments, or 4.562 shipments. 4.5 0.62. That'd be the expected number. Okay. All right. Let's do one last fresh example here. Kind of finish out getting some familiarity with the binomial distribution. In this problem, it is conjectured that an impurity exists in 30% of all drinking wells. It is conjectured that an impurity exists in 30% of all drinking wells in a certain community. 10 wells are randomly selected for testing. 10 drinking wells are randomly selected for testing. Couple parts here. Part A. First, what's the probability exactly 3 tested wells have the impurity? Probability exactly 3 tested wells have the impurity. Okay. Exactly 3 tested wells have the impurity. So this is just exactly 3. So this is a standard binomial distribution question. What's the probability that x is equal to 3? How many trials do we have here? 10 wells are randomly selected for testing. We need 3 successes. What's our success probability? In this case, it's a 30% chance that a drinking well has an impurity. So we've got 0.30. 3 of those. That means our failure probability is 0.7. And how many failures do we have? If 3 are successes out of 10, the other 7 have to be failures. So we should be looking at 10 choose 3 times 0.3 cubed times 0.7 to the 7th. And that's about 0.2668 is what I've got rounded off there to about 4 decimal places. A pretty standard binomial question there. Part B is really what I want to look at and spend some time on. What's the probability that more than 3 wells are impure? What is the probability that more than 3 wells are impure? More than 3 wells have the impurity. So in this case, we want more than 3. More than 3. This is strictly greater than 3, right? This should not be greater than or equal to. We are not including 3. Strictly more than 3, right? 3 would not count. So we're looking at 4, 5, 6, 7, 8, 9, or 10. Again, like we mentioned in the previous video, when you get these questions that involve things like greater thans, you might want to take the complement. So what's the complement of more than 3? That would be the probability that x is less than or equal to 3. Right? The complement of getting 4, 5, 6, 7, 8, 9, or 10 would be to get 0, 1, 2, or 3. That's the complement, so we're going to subtract that probability from 1. And here we go. 1 minus the probability that x is less than or equal to 3. And here you go. Look at this. This is, we should think, table. CDF. Probability that x is less than or equal to 3. With a success probability of 0.3. So we have, we're looking at our table. We've got n equals 10 trials. R is 3. So let's go ahead and go over to our table. We are looking at what here now? We're going to be looking at 10 trials. 10 trials and 3 successes. What's our success probability here? 0.3 would be right here. R is 3, N is 10. I've got 0.6496 there highlighted, right? N is 10, R is 3, success probability is 0.3. So 0.6496, there we go. Looks great. And so that is 0.3504. You subtract that from 1, and that would be the desired probability. Probability of more than 3 wells are impure. 1 minus the complement probability. And there we go. All right. The last thing I want to mention is some of you might be asking, is there a nice convenient way for me to maybe look up a value like this in a table, the probability that x is equal to 3? And I'm going to say, well, sort of, because you might recall some of the properties of the cumulative distribution function, especially in the discrete case. What's the probability that x is equal to 3? Can we write this in terms of the CDF? The probability that x is equal to 3 would be the probability that x is less than or equal to 3, right? Minus the probability that x is less than or equal to 2, right? If I want just 3, then I want, remember, less than or equal to 3, this would contain 0, 1, 2, or 3. And we're going to subtract from that, getting a 0, a 1, or a 2. So if I subtract the zeros, I subtract the 1, I subtract the 2, all I'm left with is a 3. And the reason why I'm pointing this out is because these two I can look up in a table. These two we can look up in the table, right? We know that the probability that x is less than or equal to 3 is 0.6496. And we could go ahead and look up in the table, what's the probability that x is less than or equal to 2? So that would be the same area, just r is equal to 2. So that would be the next entry above it. N is 10. Now we have 2 successes, 0.3828. And we do the arithmetic there. Sure enough, we're going to get 0.2668. Same as we had there. All right, so you can do those binomial probabilities in 2 ways, strictly using the table. Something to be aware of, kind of maybe a nice, neat little trick that might be useful.